Let's start by thinking about this. 4 times x to the third. Remember, exponents just keep track of how many bases are being multiplied. Only the x is the base. So that means 4 times x to the third, which means this. That's good. When we get to scientific notation, when you see something like 4 times 10 to the third, it just means 4 times 3 tens multiplied together. If we look at multiplying this power times this power, then this means 4 times 3x is multiplied. This means this. So check it out. Isn't it true that we can just say, well, let's multiply the 4 and the 5 together right here, and then we know that we end up with all these x's being multiplied. So in the end, the 4 times the 5 is going to give us 20, and we know we're going to end up multiplying 7 of the x's together, so our final answer is 20x to the 7th. But we don't want to write all this stuff down. I just do that to remind us what all this implies. The shortcut is simply to go back up here and say, okay, we have factors. We have a 4 that's being multiplied and a 5 that's being multiplied. Let's first multiply those together, and that gives us the 20. And then let's keep track of how many x's are being multiplied, and the answer is 7, so we can go right to this answer right here. So when you have two scientific numbers, two numbers that are in scientific notation, and you multiply those together, it's the same thing. We have one 4 that's a factor that's being multiplied, one 5 that's a factor that's being multiplied, and we have 7 of the 10s that are being multiplied. So the shortcut is just to do the same thing as we did over here. 4 times 5, that's 20, and we're going to end up multiplying 7 of the 10s together, so it's times 10 to the 7th. Okay, now let's think about this. This may look ugly at first, but this is our decimal system. When we can have the 10 to the 4th column, the 10 to the 3rd, 10 to the 2nd, 1st, 0, etc. So what's 10 to the 4th? That's 10,000. 10 to the 3rd is 1,000. That's where all these place values are. Remember, anything raised to the 0 power is 1. And then over here, if we have 10 to the negative 1, that's the inverse of 10, so it's 1 over 10. So these are like dimes, and those are like pennies. So suppose you have a paycheck, and you get a paycheck for $3,428.62. How do we know that's what it's worth? Because this is in the ones place, the 10 to the 0 power. This is in the tens place. This is in the thousands place. And we know that these are dimes and pennies because that's the meaning of 10 to the negative 1, 10 to the negative 2. 10 to the negative 2 is the inverse of 10 squared. It's 1 100th. Those are pennies. Now, if we added this up, what we're really doing to get the value of this number, we just memorize that that's the thousands, that's the hundreds. But what we're really doing when we're saying, hey, I believe that that is worth 3,428.62 hundredths, is we're saying, well, we have 3 times 10 to the 3rd here, plus, let's add the 4 $100 bills, plus 2 $10 bills, plus 8 $1 bills, plus 6 dimes, plus 2 pennies. And that's our answer. So it's scientific notation is really what we're doing, and we don't even really realize it. But remember, if we're adding these powers together, we're not adding the exponents together to simplify. We're just saying it's this plus this plus this, and you leave it alone. Contrast that with this, though. What if we had a rabbit that had 3 times 10 to the 3rd kids? You talk about multiplying those rabbits, okay? And each kid had 4 times 10 to the 2nd friends, and each friend did 5 times 10 to the 2nd homework problems. All right, so how many homework problems would the friends of the kids of this rabbit do? Well, the rabbit has this many kids, 3 times 10 to the 3rd. Each kid has 4 times 10 to the 2nd friends, and each friend is doing 5 times 10 to the 2nd homework problems. So how many homework problems is that? Well, think about our factors. Things are being multiplied. There's 1 3 being multiplied, 1 4, and 1 5. But how many 10s are being multiplied? 3 here, 2 here, and 2 there. So altogether, there's 7 10s that are being multiplied. So we can go 10 to the 7th. And then we have 3 times 4 times 5. 3 times 4 is 12, times 5 is 60. So we have 60 times 10 to the 7th homework problems that are being done. Now, by the way, if you do your homework, you should be able to find a job, because look at all the homework problems these rabbits are doing. And have you ever heard of a rabbit being unemployed? I rest my case. All right, now here we go. Let's try these guys. How much is 5.2 times 10 to the third? Let's think this through. 10 to the third is 1,000. So if we have 5.2 thousands, then we have 5,200. So what do we do with this decimal place to change something in scientific notation to this number? The shortcut is to move the decimal according to the power of 10. We're multiplying by 10 to the third power, so in essence, it moves the decimal 3 places. 1, 2, 3 places over, and put a couple zeros in there, 5,200. Now what about this? What if it's 5.2 times 10 to the negative third? Then if we follow that line of reasoning, we should be able to move this decimal over 1, 2, 3 places and put zeros to cover it. So our answer should be 0.0052. Now, why does that make sense? Check this out. Let's do this another way. This is 5.2 times the inverse of 10 cubed. That would be 5.2 times the inverse of 10 cubed, which means to multiply by 1 over 10 cubed. So this would give us 5.2 divided by 10 cubed, which is 5.2 divided by 1,000, or 5.2 thousandths. That's what this is. Get the 5 in the thousands place, 5.2 thousandths right there. But the trick is move the decimal according to the power. So we'll move the decimal 3 places to the left, boomity boomity boom. Or in this case, 3 decimal places to the right, boom boom boom. Fill in with zeros as you need to. Keeping that in mind, we get the definition of what it really means to have a number in scientific notation. It needs to be in this form here, a number times 10 raised to some constant. But that number, that A, has to be a number between 1 and 10, closed on this end, open on this end. So check it out. These guys would both be in scientific notation because the number we're multiplying the power of 10 by is a number that's somewhere between 1 and like 9.999. These are okay. This guy's no good because this number being multiplied by the power of 10 is bigger than 10, and we need our number to be between 1 and 10. So no problem. Here's what we do. We need to, if you think about this, do this a couple ways. This is 12.9 times 100. So this is 12.900. Doesn't that mean it's 12.900? Isn't it equivalent to 1,290? Well, if we're going to write this in scientific notation, we need this decimal to come over 1, 2, 3 places. So we can write this as 1.29 times thousandths times 10 to the third. We move the decimal 3 places, so we need to compensate with a 10 to the third power. Simpler way to do it. But let's look at 2 simpler ways to do it. Okay, whatever sticks. Now check this out. If we're going to move this decimal 1 place to the left, we have to compensate by increasing this power by 1, so make it 10 to the third. But why did that work? Okay, so let's do this. Let's say, okay, we had 12.9 times 10 to the second power. And I love it if we can remember that the most important number in all of mathematics is the number 1. If we're going to change this number so that it is a number that's between 1 and 10 like it's supposed to be, then the way we end up moving the decimal over 1 place is by dividing this number by 10. But if we just divide the number by 10, we've made the number 1/10 as big, and that's no good. So what do we have to do to compensate for dividing by 10 to change it to this right here? We need to multiply the numerator by 10. So that what we're really multiplying 12.9 by is 10 over 10, which is equal to 1. We're multiplying by 1, so we haven't changed the value of it. So what we have then is this guy becomes 1.29, but we're still multiplying by 10, and then we're multiplying by this 10 squared over here. So altogether, how many 10s are being multiplied? Those 2 plus this 1. So that is really the justification for why you can go from 12.9 times 10 to the second to 1.29 times 10 to the third. But the shortcut is, if you move the decimal 1 unit this way, you need to compensate for division by 10 by multiplying by another power of 10. So if you move the decimal point 1 point this way, kick up or increase that power by a value of 1. So then, well, by golly, so what happens with this? What if you had 129 times 10 to the second? No problem. What we do is we take this decimal, and if we move this decimal over 2 places, don't we have to compensate division by 100, which is what we did there, by increasing this power by 2 and making it 10 to the 4th. So 129 times 10 to the 2nd is equivalent to 1.29 times 10 to the 4th, and now we have it in scientific notation because that number is a number that's between 1 and 10. And then finally, I think this is it. Yep, last problem. If we multiply this guy by this guy, well, again, we have a bunch of 10s being multiplied. We have 8 of them. 3 here and 5 more there. Now let's just multiply these two other factors. When we multiply those together, we get 24.1664 times 10 to the 8th. Okay, that's true, but it's not in scientific notation. So the last thing we need to do is make sure this number becomes a number between 1 and 10, so we could write it like this. But what did we do to change 24.1 to this? We divided by 10. To compensate, we better multiply by 10 and kick up this power of 10 one more to make it 10 to the 9th power. Scientific notation.